All right, so today we're going to talk about absolute value inequalities. All right, so absolute value inequalities are very similar to absolute value equations, which we did not too long ago, I think end of last week. So our steps are going to be pretty much the same, okay? We're still going to isolate the absolute value using PEMDAS backwards, or undoing. That was the same as the first step with the equations. And then remember, when we isolated the absolute value, we wrote two equations, one where the right side was positive, one where the right side's negative. We're doing the same thing again. We're still going to isolate, once we isolate that absolute value, we're still making, in this case, two inequalities, one where the right side's positive, one where the right side's negative. But now, the only other difference is, since we're talking about inequalities, the side where the right side is negative, we have to flip our inequality also. Okay, that's really the only difference. That we'll have an inequality to start, and when we make that right side negative one, we would flip our inequality. And then we have two pretty basic examples here. So when we have the absolute value is less than 4, so that means it would be less than 4 units on either side. So again, remember, absolute value means distance from 0. So I could be 4 units to the right and 4 units to the left. And if it's less than 4, that means my shading would be where then? If I'm picking an x value that's less than 4 units away from 0, shading would be in the middle or on the outsides? In the middle, because 2 is less than 4, right? 0 is less than 4. Negative 1 is less than 4. So your shading would be in the middle here. And so essentially, your answer here would be parenthesis -4 to 4. Where if we wanted our absolute value of x to be greater than 4, we would still have open dots at -4 and 4, because that's our distance from 0, 4 units away from 0. But if we want that value to be larger than 4, then our shading would be pointing outward, because we want numbers to be, our distance to be larger than 4. So out here, like 5, 6, 7, 8 is larger than 4. And so in this case, since it's two separate going out, I would have to write two separate inequalities. So it'd be -infinity to -4 union 4 to infinity. Okay, so those again are the most basic. Now we'll kind of make them a little bit more complicated. All right, so our first one, it says absolute value of x minus 2 is less than 5. So again, our first step is always to isolate that absolute value. That is done for us already. So now that it's isolated, again, just like the equations, we're going to make two separate, in this case, inequalities. So I have x minus 2 is less than 5. That's not changing. Okay? That's just dropping the absolute value. Everything's staying the same. Our other inequality, again, drop the absolute value. So I have x minus 2. We make that right side negative, and because we made that right side negative, we had to flip that inequality. So here we will add 2 So we get x is less than 7. X is greater than -3. So on our number line, 7 would be over here. We're going to have an open dot on 7. -3 would be over here. Open dot on -3. So the shading is always either in the middle of the two dots or pointing outwards from the two dots. So we want to figure out where's our shading going to be. We want our x to be less than 7. So that's going that way. Greater than -3. So that's going in the middle. So our shading's in the middle. Your shading should never go in the same direction. So if I said less than 7 and I forgot to switch my inequalities and it was less than -3, that doesn't make sense to me. So you want to kind of use that as a guide. If I saw both shadings were going to the left, you'd have to go back and check your work because somewhere there's a mistake. So now that we know our shadings in the middle, our interval notation, parenthesis, -3 to 7, parenthesis. All right, try that one on your own. All right, so again, our absolute value is already isolated, so that's done for us. So we can go ahead and write two inequalities. First one's x plus 3 is greater than or equal to 4. Second one would be x plus 3 is less than or equal to -4. Okay, so from there, we would subtract 3 and get x is greater than or equal to 1. Subtract 3. X is less than or equal to -7. So we have 1 with a closed dot, -7 with a closed dot. All right, if we want our x to be greater than 1, that means our shading's over this way. And again, in our mind, we know that the shading's either in between or pointing outwards. So since this shading is to the right, we should know that this shading's going to be to the left. And we're going to double check to make sure it actually is going to be shaded to the left. X is less than or equal to -7. Yes, it does. So we knew our sign was right. If I forgot to flip my sign and it was x is greater than or equal to -7, again, something's off. You want to go back and check your work, make sure you flip that sign. All right, so then how do we write this in interval notation? Since it is two separate, we'd have to write it as -infinity to -7 with a bracket, our union symbol, bracket 1 to infinity. All right, so let's just try 68 for right now. All right, for 68, that absolute value is already isolated. Okay, there's nothing outside of the absolute value. So right away, we can go ahead and write two separate inequalities. And again, we make the right one greater than -6 then. So as we go to solve this, first thing I want to do, since this whole thing is divided by 4, the opposite of division by 4 is multiply by 4. So I can multiply this side by 4, and then I multiply the other side by 4. So that 4 cancels the 4's out. So we're left with 3 times the quantity of x minus 1 is less than 24. Now, if you wanted to, you could distribute that 3 through, but since that 3 is in front being multiplied, I think it's just as easy to divide by 3 right away. So that's what I'm going to do. If you decided you wanted to distribute, there's nothing wrong with that. It's just kind of an extra step. So that's going to give me x minus 1 is less than 8. And when I add 1, I will get x is less than 9. On the other side, same idea. I have to multiply by 4 first to get the division by 4 out of there. So that 4 is canceled. So we get 3 times the quantity of x minus 1 is greater than negative 24. Again, we would divide by 3. And we get x minus 1 is greater than negative 8. And so we would add 1. X is greater than negative 7. Okay, so 9 would be here. Negative 7 would be there. Open dots on both. Less than 9 would be pointing to the left. Again, since we know this one's going to the left, we should make sure that the negative 7 is pointing to the right. X is greater than negative 7. It is. So we know we did it right. Shading's in the middle. And then we'd have parenthesis, negative 7, 9 parentheses. All right. So again, that was just a little bit harder on the inside. That's why we did that one. The inside solving it was a little harder. Now, if we look at checkpoint 9, now there's some other stuff around the absolute value. So that's what's different about that one. So again, first step is to isolate that absolute value. So we're doing PEMDAS backwards here. So I undo the addition subtraction first. So this plus 20, I got to undo that first by subtracting 20. So I get negative 39 on the right side. Remember, you can't distribute through an absolute value. We got to keep undoing. So we're undoing the multiplication with division. So we're dividing by negative 3 on both sides. Remember, all that does is cancel out the negative 3. We still have the absolute value, and what's inside the absolute value is not being touched. And that would give us positive 13. Okay, that absolute value is now isolated, so we can go ahead and write our two inequalities now. So 5x minus 2 is greater than or equal to 13, and 5x minus 2, switch our inequality, less than or equal to, make our right side negative. Yeah. Yes, I did. Thank you. Perfect. I forgot about that one. So because we divided by a negative here, we also have to flip our sign originally. So that means we're going to change our signs, all of them. Thank you, Nathan. So I've divided by a -3 here, so I have to flip that sign to less than or equal to. And then because I'm going from there, I'd have less than or equal to, greater than or equal to. All right, so here, as I go and do that, I'd have to add 2. We get 5x is less than or equal to 15. Divide by 5. And we get x is less than or equal to 3. And then when we add 2, that would give us -11. And we divide by 5. X is greater than or equal to -11 fifths. All right, so -11 fifths is on the left. It would be a closed dot. And then +3 is on the right, again a closed dot. And we want it to be less than 3, greater than 11 fifths, so that's shading in the middle. So bracket -11 fifths. Three, the bracket. All right, we're almost done. All right, so we got checkpoint 10 here. All right, so notice for this one, our absolute value is on the right and the x is on the right. Remember what I said yesterday. It makes your life a whole lot easier if your x is on which side? The left or the right? The left. So let's make our x on the left. So I'm going to move, kind of switch sides here. I'm going to make this 6 minus 3x absolute value on the left, 18 on the right. Now, you can't just move things around without caring about the absolute or the inequality. So if you remember from elementary school, the little alligator, notice the alligator is biting the absolute value, right? So if I flip sides, the absolute value, the inequality, or the alligator still needs to be biting the absolute value. So I need to switch that inequality to a greater than, because the alligator has to be biting that absolute value still. Okay, so if I switch sides of everything, you're switching the inequality as well. Notice this absolute value is already isolated, so we are done with that part, and we can go ahead and just write our two inequalities. Okay, as we go to solve these then, -6, -6. So -3x is greater than 12. And when we divide by -3, we are dividing by a negative here. So we are flipping our sign. So x is less than -4. And then we do -6 on both sides. We have -3x is less than -24. And because we're dividing by a -3, our x would be greater than 8. All right, so we'd have open dots at both of these. We want it to be less than -4, so that is going to the left. Greater than 8 is going to the right. Again, shadings are always either opposites or in the middle. In this case, they're opposites. So we need to write this as two separate intervals, -infinity to -4. Our union, maybe 8 to infinity. All right, and then one last one that's a little tricky is this one here. All right, so again, first thing I want to do is I want to get my x on the left. Okay, so I'm just going to switch sides with everything. That's what I always recommend you doing first, making sure your x is on the left. And remember, the alligator is biting the absolute value side, so when I rearrange our sides, the alligator still needs to be biting that absolute value side. Okay, now I can start doing PEMDAS backwards, so I undo the addition of 7/3 with subtraction of 7/3. So I get the absolute value of x minus 11/3 is greater than. So I need to think of this in terms of thirds. Okay, 1 is equal to 3/3. So I'm doing 3/3 minus 7/3. What's 3/3 minus 7/3? -4/3. Remember, you need a common denominator, which we have. We just subtract the tops, keep the bottoms the same. Now, if you notice, that absolute value is isolated, right? And it has to be greater than a negative number. Okay? So when we take the absolute value of anything, what's going to come out? Positive, right? So what's going to come out of here is always positive. So is a positive number always going to be greater than a negative number? Yeah. So what can we put any number in for x, or does that have to be a special x that's going to work here? It could be anything, right? I can put any number in for x, subtract 11/3, and I'm taking the absolute value of it. It's going to be greater than any negative number. So our answer for this one would be our all real numbers. So we can say -infinity to infinity. And again, on a number line, that would then just be everything shaded. So When we did absolute value inequality, when we did absolute value equations and the right side was negative, we said there was no solution because there's no way the absolute value can be negative. But now it's an inequality. Well, anything that's greater than a negative number is always going to be true. So that's why that one's just a little bit tricky there.